So welcome back. In our last video we were done with BST, and now we'll move a step forward, that is your AVL tree. Now this particular name has come from the people who are behind this AVL tree, because it was invented by G.M. Adelson Wellesley and E.M. Landis. So it was named as AVL tree. Now there are some properties of it, and we'll see that how this particular BST is this particular AVL tree is better than your BST. Now to start with, these are some of these basic properties of AVL tree. One is that it is also known as your self-balancing BST, right? So once again you can say that it is nothing but a variant of BST. So that means it will have either 0 child or 1 child or at most 2 child with some additional properties. So the heights of 2 subtrees of a node can differ by at most 1. In case of AVL trees, the height of 2 subtrees of a node may differ by at most 1. And since we are looking for the height, so this particular thing is also known as height balanced tree. And in some of the literatures you will also find it as height balanced BST, right? So both the things are same. Now one of the major advantage of using this BST is that all these 3 operations, which is search, insert and delete, can be performed in order log n time. That means the time complexity is order log n, right? Whereas in case of BST, your time complexity for all these operations is order n, and the algorithm with lower time complexity always wins. So that's something which is a major advantage of using AVL tree over your BST. As I said, it is nothing but a height balanced binary search tree, so it is nothing but a variant of it. There were some issues in binary search tree. In one of the video I had a discussion on it as well. Let me try to explain you with the help of an example. That we said in case of BST, your order and the key values matter, right? Based on the order and based on the key values, I may see different size of my binary search tree. So let's say I have a binary search tree with the key values as, let's say, 1, 2, 3, 4, 5, 6. And this is the order of inserting the key values or the node values to the binary search tree. In this particular case, my binary search tree will look like this: 2, and then 3, and then 4, and then 5, and then 6. Right. Whereas if suppose I bring some changes, let me bring some my random changes 4, 3, 2, 5, 1 and 6. Same set of key values, but yet a changed order, that would result into, let's say 4 comes here, now 3 will come here, 2 will come here, and then 5 comes here, and then 1 comes here, and then 6 comes here. Now if suppose I have to search for an element which is 6, in this case it would be nothing but a linear search. In this case, in some sense, it's a kind of binary search. So 6 comparisons in this case, whereas only 2 to 3 comparisons in this case. So just see the difference in the working of these two binary search trees, just because of the virtue of the order and the key values, right? Although the set of key values remains the same, but yet since the order got changed, so the number of comparisons are lesser in the second case, whereas the number of comparisons are higher in the first case, right? So this is something which is a major drawback of binary search tree, or else for search factor it works very well, right? As far as search is concerned, it works very well. Now, so there is something called as balance factor. So that is an additional point added to my AVL trees. So in case of balance factor, each node of the tree will have a balance factor which will range from -1, 0 or 1, not more than that. And if suppose my balance factor comes out to be something which is outside this particular set, in that case what I'm supposed to do is I'll declare that the tree is not an AVL tree, right? So this is one extra property of my tree, and that's why we call it as AVL tree or a height balance tree. So each node has a balance factor which is nothing but termed as BF in some of the literatures, which should be in a range of this. And how to identify this particular balance factor, which is the height of your left subtree minus height of your right subtree, right? So let's take one example where we'll find the balance factor of each and every node, so that would make the things much more clearer. Now, how to identify the balance factor? So let me take one random example. Let's say I have something called as 50. I have something for sure lesser than 50 will be on this side, and this side I have 47. This side I have let's say 80, and once again this side I'm getting something called as 70. This side I'm getting 100. So let me add 120. Right, now let's identify the balance factor of each and every node, right? So the idea is to identify the balance factor for each and every node. So height of, in this particular node, height of left subtree minus the height of right subtree. Alright, so this comes out to be, let's say, 2 minus 3, which comes out to be -1 in this case. So this is within the range of -1, 0 and +1. So this particular thing is okay. In this case it is coming out to be 1 minus 1, which is your 0. So this particular thing is also okay. So this particular thing once again, 0 minus 0, which is 0. So this particular thing is also okay. For this it remains the same. This is okay, and for this it is let's say 1 minus 2, which is -1. So once again I am perfectly fine with this node as well. Now this once again is nothing but 0. So this is like 0 minus 1, which is -1. This is also fine. This comes out to be 0. So this is a height balanced binary search tree, which is nothing but your AVL tree. Now, for identifying whether a particular tree is an AVL tree or not, we have to go through this particular exercise every time. And if suppose you identify that for every node my balance factor is either -1, 0 or +1, then I'm good to declare that this particular BST or binary tree is nothing but a height balanced binary search tree, which is nothing but your AVL tree. So in order to make you understand, what we say is that every time a BST, which is your binary search tree, plus this particular height condition gives you nothing but an AVL tree. We see that there are various advantages of this AVL tree over your binary search tree, but yet there are some drawbacks associated with this, because in order to achieve this particular condition of balance factor, I need to come up with a code which is much more complex, right? So that means the code for your AVL tree is much more complex than the code for binary search tree, because we have to handle a lot of corner cases, right? That particular thing will be much more clearer when we'll talk about rotations, because in order to make a binary tree an AVL tree, I need to perform certain rotations. Those rotations I'll be covering in my next video. And since this coding is somewhat complex, this deletion operation cost is high in AVL trees, as lot amount of pointer changes and rotation takes place. And every time I need to maintain the height, because it's also called as your height balanced binary search tree. So the frequent rotations are done, which in turn increases the pointer overhead, which even tends to some negligible extra space for very big input size if my data size is huge. But considering today's scenario where the computation cost is very low, just because we have very high potential processing power, in that case what we do is that particular part we neglect, right? So comparatively it's like insertion and deletion is very slow in case of AVL tree. That's something which is a major drawback of this particular algorithm, or else it is something which is preferred and works very well. So in our next video, we'll talk about rotating and converting, or maybe you can call it as adjusting the balance factor in order to come up with an AVL tree or the height balanced tree. See you in my next video.